Yeah. So if people have to ask any questions, so there's a question and answer tab. What you can do is towards the end of the seminar, we are reserving at least 15 minutes for question and answers. You can, press the question and answers and then ask your questions, and we'll be able to answer you those questions. Yeah. So a lot of more people are joining. So let's just keep waiting for some more time.
Asif, I think we should start.
Yeah, we can get started. Okay. So welcome everyone. Welcome to the I3C seminar from Prodigy Technovations. I am Asif. I'm the host for the evening. So I'll be helping you through the seminar as you go through. So with me, I have two extreme experts panelists. The first one is Godfrey. Godfrey has 25 years of experience in test and measurement. He was working for Tektronix and later on worked for HP. And from the last 10 years, he's been running Prodigy Technovations, right, in Bangalore. And Godfrey, you want to say hello? Yeah.
Yeah. Hi, everyone.
Yeah. So Godfrey, so that's Godfrey there. And with Godfrey, we have another expert, Brijesh. Brijesh, you can turn on your mic here. Yeah. So Brijesh has around 5 years of experience. So he's done pretty much the entire coding of the I3C RTL. He's the technical expert here in terms of implementation of the I3C. Okay. So a couple of rules for everybody to understand. Brijesh, you want to say hello? Yeah.
Yeah. Hi, everyone.
So yeah, a couple of rules here. So as this is a webinar and people will not be allowed to ask questions on the voice. What we have is we have a Q&A tab here below. So what you have to do is at the end of the seminar, go to the Q&A tab and press your question and answers. And you can type in your questions and we'll pick the questions one by one and we will give the answer. Okay, with this, what I'm going to do is I'm going to hand over to Godfrey. Godfrey, you can take over the session from here.
Thank you, Asif. So thanks everyone for joining this session. So let me get started with the I3C Protocol Basics and testing of I3C devices. So what I'm planning to discuss myself and Brijesh is that just one slide on about Prodigy Technovations, since we are almost a new company in this domain, but we have been in business for last 10 years. We will have an overview of I3C interface, like introduction and the protocol operations and how does I3C works with the DDR5 and some of the key features of maybe I3C. And then we go into the testing of I3C devices and systems, like what is required to test a master, slave, legacy, I2C slave, and emulate a I3C bus, right? So these are the kind of a complete agenda for the next 1 hour. So this is, I'm going to talk about it. So about Prodigy, we started in year 2009. We are headquartered in Bangalore in India, okay? So we are based out of India, but we have distributors to reach out to, like, to buy our products in US, Japan, Korea, Taiwan, France, Germany, China, Israel, Italy. So almost every geography we have a distributors, and they are all very well trained, and most of them are with a similar product background, so they could able to support you very well. And we started our journey in year 2009, as I mentioned, developing software applications for a Tektronix oscilloscope. Like as Asif mentioned, I am a previously employee of Tektronix, and that's what excited me to develop some new products for Tektronix scopes. And when we went to the customer with these applications, people did buy, and they still continue to buy these applications from Prodigy. But then there were some of the requirements. They wanted more capabilities and debugging features. So that's when in year 2014, we started developing a hardware-based protocol analyzers, okay? And we launched our first protocol analyzer in year 2015, that is eMMC SD SDIO. Now we have a portfolio of protocol analyzers like UFS 3.1. It runs at 11.6 gigabits per second per lane. It's a two-lane technology. And then we have a 100 base T1 automotive Ethernet. It has a unique 5-layer. Then for MIPI, I3C, RFFE, SPMI, we have an exerciser and protocol analyzer. Then we recently launched a very new logic analyzer. It's a 10-channel logic analyzer with a high real-time sampling, 1 giga samples per second. And we can do I2C, SPI, you are triggering. It's a hardware-based real-time trigger you can do based on the packet content, and also you can decode them. And then we have now I2C, SP, SM bus, and SPI exerciser and protocol analyzer also. So we continue to develop applications for Tektronix oscilloscope. We have a range of softwares for different interfaces. They are listed out here. And you can really know about Prodigy Technovation by visiting prodigytechno.com website. So what was happening here? Why I3C is emerged, and what was currently many of us are using is I2C and SPI bus, right? So if you look at the I2C bus, it's a multi-drop bus with one master and a few slaves. And the slaves are all connected to the master using a clock and data line. It's a 2-wire bus, but there are also few interrupt lines. Okay, there are few interrupt lines, so which will means that the master must have more IOs to take care of those slave interrupt lines, because whenever a slave has something to communicate, which is a priority, it has to send out those interrupt lines and access the master, and master can read those data. So the maximum speed I2C can go up to is 3.4 megabits as per I2C specification. But what I've seen is that most of the devices which work at 1 megabits per second. That's the speed what I2C is supporting. And people who wanted a higher speed, they adopted a SPI bus. And SPI bus is like was like had a 4-wire signaling like clock and chip select, MOC and MISO. And so it's a more IOs are required, but it can go up to 40 to 60 Mbps per second. But then the protocol implementation varied from vendor to vendor. So it brought in its own challenges because of there is no rigid following of the standards. So there was kind of one has to really work with the master devices, the slave guys, or with the slave to make sure the interoperability is maintained. Now, definitely there was a more demand for higher speed, and that's where MIPI pitched in, and MIPI came up with a specification I3C bus, and there's a lot of excitement and a lot of people are adopting it now. So it could go up to a data speed up to 33 megabits per second, and it has a different modes. We'll look at it details later. Some of the key features like in-band interrupts. Now, if the slave has to communicate, there was no additional line was required, so it can just send an in-band interrupt on the same data line, and it can tell the master it has to send some data. And so naturally, it got a less number of IOs in order to just clock and data lines, and it could support a data rate. It's a flexible. You can go from 1 kilobits per second all the way to 33 megabits per second. And also got early adopters, mainly adopted by sensor interfacing and DDR5 for PMIC and SPD kind of devices. So that's the I3C, like how it slowly is trying to replace I2C and SPI bus. And it is a standard, very well defined, and it's managed very well with the interoperability, making sure all the devices and slaves are working. So I2C interface, as I mentioned, right, it is a improved version of I2C and SPI, and it's a 2-wire bus. So naturally you need a less number of IOs, and it's a standard multi-drop interface with the host processor and peripheral sensors you can connect. So some of the key features, why it is also important is that as the number of data rate goes high, the energy required to transfer this data is less. So you could use less number of edges to send the same more amount of data between the host and the slave, master and slave. So again, it has a reduced number of pins, which is a great advantage for the packaging industry and the PCB designers. So they can now manage things with just 2 IO lines. And it's a 2-wire serial interface going up to 12.5 megahertz clock speed. And it also, good part is that it supports the legacy I2C devices. So you have enough time to change over from I2 to I3C. And there are a few things you would like to use and continue to use I2C. The I3C standard accommodates that. And dynamic address supporting is available. So dynamically we'll assign the address, and the data transfer, the learning curve is also very short because the data transfer rate and the data packets are very similar to I2C. And optionally, you also have a higher data rate, which is available in certain standard, and also it's a multi-drop, multi-master, in-band interrupt, and hot join capability. Hot join is another interesting feature of I3C, which will make this like standard and encompasses and addresses the most recent and the upcoming requirements in sensors and the new system design applications. So let's look at the status of the specifications, like which version or what's available. So currently there is I3C 1.0 version is already in the market. This is the first release done by MIPI Alliance. And this is, I think, announced almost in around 2018 timeframe, in my opinion. And it goes up to it's a 2-wire bus in I3C version 1.0. Now, then there is a lot of people wanted to use this in many applications. So the MIPI Alliance came up with a I3C basic specification, which is in a public domain. The companies which are not member of MIPI Alliance, they can still access this I3C basic specification, and then they can go ahead and develop their products. And now recently in the year 2019, MIPI Alliance says, keeping the future requirement in mind, so they announced I3C version 1.1. Some of the key requirements here is that the features of I3C version 1.1 over version 1.0 is multi-lane support. So you have a 1 clock lane, 4 data lanes. So naturally you may be able to go up to 100 megabits per data speed. And they added some new additional commands based on the experience on I3C 1.0 to accommodate some more different applications. So I3C basic specification, as I mentioned, it's in the public domain. But we would like to inform you that some of the things which are not there in I3C basic specifications compared to I3C version 1.0 spec is the timing control, HDR double data rate, the DDR mode is not covered in I3C basic specification. And then there is a very interesting data mode called ternary symbols, TSB, which is basically minimizing the number of edges and using the clock and data lines and extending the data rate up to 33 megabits per second. So which is also not part of the I3C basic specification. And what is available in I3C basic compared to I3C version 1.1 feature, what is available? So the I3C basic specification also covers some of the direct read and write common command code commands, and get maximum data speed refinement. They are able to do it. And there is something called set ASA. This is a command for address assignment. I think my colleague will talk about it more in detail later. And also it has something called low voltage high capacity load IO for the physical layer side. So these are some of the main difference with I3C basic. And in case you would like to know about more detail about I3C version 1.0 spec or 1.1 spec, so we would request you to contact MIPI Alliance. So the fundamentals of I3C is very similar to I2C. The fundamentals do not change so much. That's a big advantage in my opinion, because it gives you early adoption cycle reduces. So that is not so much complicated to adopt this I3C specification. So it has a SDA bidirectional data line, and it's a clock line. It's going from the master to slave or master to devices. And then I3C, the packet format is very similar to I2C SDR messages, like the start and stop, address, read, write bits, all those things are very similar to I2C. So you will find it very convenient to get understanding of the I3C specification. Then in order to make a broadcast or a public announcement of the information from the master to all the slaves on the I3C bus, there are broadcast commands are available. And if you want to communicate to the specific slave, there are different direct commands are available. And then there is a HDR mode messages. Then you have a legacy I2C support is available. So you have I2C messages are also available. So slave also can make some initiate some requests in the form of a in-band interrupt, and also some hot join requests they can put up so that they can come and join the I3C bus. So the data rates, as I mentioned, is going up to 12.5 megahertz is a clock speed. There is a data coding, which is I3C data coding, which is a single data rate SDR mode. And the same data is also supported with the direct addressing, common command code direct addressing, and the broadcast addressing. Now, then you have the high data rate. It's a DDR mode. There are 3 modes are available for DDR, which are mainly available on I3C version 1.0 specification. It is not part of the I3C basic, as well as I2C legacy devices no need to support these data modes. So they are called HDR mode, high data rate, dual data rate mode. And then there is a ternary symbol legacy mode and ternary symbol pure bus mode. So these are the additional data modes are available with the I3C 1.0 and 1.1 specifications. So now let's look at how does the protocol works, I3C protocol works, right? So once you have the I3C bus network, there is a need to configure that, right? So you have the slaves and you have a master. So we need to configure like what are the capabilities to the I3C. Like you really no need to have all the I3C slaves which are on the I3C bus. There is no need to support all the capabilities. It may be just with SDR mode or maybe HDR mode, and some of them may support in-band interrupt, some of them may not support in-band interrupt, and some of them may have a limitation in the data speed. So all these configurations needs to be done in an I3C bus. Then you have a communication methods. How do we initiate the communication from the power on state? How does the master works with the slave, and how does the slave works with the master? So that's the communication modes. So we have to have a proper rule sets to do that. Then there is a bus free condition, like when there is no activities going on the bus needs to have a low power consumption. So whether we have to pull up the bus and all those things. How do we assign the addresses? So hot join mechanism, how does a slave can join the already existing I3C bus and all those things? How do we set the priorities of the slave? So then in-band interrupt. And there is also a unique feature, something called peer-to-peer peer lane communication is also available, and different commands. This forms a different, the protocol format for the I3C. Then when it goes to the HDR mode, like you need to look, that the device can enter into a HDR mode with sending some known pattern as per the I3C specification, and then complete the task and then exit out of it by sending exit pattern end of it. But these are all well defined in I3C 1.0 specification, and also there is a TSP and TSL specification. So you will need to find all those more details about HDR by going through the I3C version 1.0 specification. So that's about the protocol. The key characteristics. Now, how do we define the bus configuration, right? That's the important part. So to set those values, there are 3 registers are provided, like bus characteristics register, device characteristics register, and provision ID, PID we call it. So there are different bits are set for different functions. By controlling those bit values, one can really configure the slave and the master to based on the application requirement and use it. Okay. So then you have a legacy I2 devices are supported. They also can be accessed on the bus. Now, how does the communication start? Like as I mentioned, I3C supports as a I2C There is a SDR mode, then there's a SDR broadcast, SDR direct messages, and then there is a HDR mode. So all the communications is in a frame format. Okay, so when I say it's a frame, there is a start condition and there is a stop condition, and in between these two start and stop conditions, you have all the protocol activities will be going on. Okay, so you can look at here in this slide, like for example, if you look at, let's take an example of I3C SDR direct messages. So it will send a broadcast, then the common command code and the direct addressing and repeated start, and it can send the data and dynamic address assignment and data. It can loop in that path and then do a stop and exit, and then again go back to the start conditions. So this is how a bus communication would take place. So now I would like to hand over this presentation to my colleague Brijesh. He will go through some of the details of I3C commands.
Thank you, Godfrey. Okay, so here there is in I3C there is a three type of commands like broadcast command, directed command, and private command. So broadcast means if on the I3C bus, if one master and three slaves are present, and master wants to communicate with all the three slaves together, so it will send the broadcast command. After that, directed command. So in directed command, if master wants to uh, send command to the particular slave, then it will communicate with the direct command. Then next is a private messaging. So private messaging is used for the data transfer mode. So master can issue private write or read to the specific I3C device. Okay. So there is a main difference between I2C and I3C is in I2C it will all the transaction will happen with respect to static address. So here in I3C there is one difference is that it will have the static address, but it will have the dynamic address also. So dynamic address mainly used for the giving the priorities to the slave. So whoever having the lowest dynamic address, it will have the highest priority. That also decided by the master. So to assign the dynamic address assignment, there are three methods are there, three commands are there. First one is enter dynamic address assignment. As you see here in the plot view, there is clock and data line. So first it will start with 7E. 7E is a broadcast address for the I3C. So all the operation, whenever master wants to send broadcast command or directed command, it will first send with the 7E. So 7E is a broadcast address. So let's say on the bus, one master and three slaves are present. Then all slave will give acknowledgement to this 7E. After that, command 7 is for enter dynamic address assignment. Then it will give repeated start, then 7E and read. So read command 7E read is only for the enter dynamic address assignment. So after that, slave will give its PID, BCR, DCR value, and in this phase, it will do the arbitration. So whoever having the lowest PID, BCR, DCR, it will win the arbitration, and master will assign the dynamic address to that slave. So let's consider this case. So after that, slave will send PID, BCR, DCR value, and master will assign dynamic address to that. After that, if it will give repeated start, and again it will give 7E read. And if any slave means, let's say three slaves are there, and one slave got assigned dynamic address assignment. So next time onwards, it will not participate in this arbitration cycle, and another two slave which don't have a dynamic address, it will take part into that, and it will send its PID, BCR, DCR value, and master will assign the dynamic address. This is first method. So next method is set dasa. So this command is used for when master wants to ignore this, means this, because enter DA will consume more time. So instead of master knows how many slaves are present on the bus and master knows the static address of that. So directly it will assign with that static address, and from that static address it will give the dynamic address assigned to that slave. After that, next command is set asa. So this is the fastest method to assign the dynamic address assignment. So in this case, whatever static address is there, that itself will become the dynamic address, and this is broadcast command. So master will just send the set asa command, and all slave will have the same dynamic address as their static address. So here one more command is there. If after some operation master thinks that I just want to change the priority for this slave, so it will give the set new DA command, and it will assign through the dynamic address assign. So slave, it is directed command. It will send set new DA command with the particular slave address, and it will change the it will give the new dynamic address to the slave. So this is an example of directed address. So it will give 7e, as I mentioned earlier. All the directed and broadcast command will start with 7e. After that, it is giving 8d, and then slave address. And after that, this is 8d is for get PID command. So there are certain registers are there in that I3C slave, like maximum read length, maximum write length, BCR, DCR, PID, get status. To read these registers, we need to send directed command to that slave, and we can read that registers. After that, this is interesting thing. Actually, in I2C, it is outband interrupt. So you required another IO to give interrupt to the master. So here it is in-band interrupt. So how it can initialize this, initiate this in-band interrupt is, slave can pull SDA line low, and master will detect that it got pulled SDA line low, and it will start giving open drain frequency on the bus, and slave will send its own dynamic address with read bit set. If read bit is set, then it means that it is IBI request, and after that master will give acknowledgement here, and after that slave can send its mandatory data bytes on the bus, and there should be, as per the mutual understanding between master and slave, if uh, in-band interrupt requested by the slave, then master can initiate some read command. So that is not defined in the spec, so that should be with mutual understanding between master and slave. After that, this is hot join process. So hot join means one slave joined after bus dynamic address assignment, and it wants to communicate on the I3C bus. So it requires dynamic address. So it will same procedure as IBI. So it will pull STA line low, and it will give addresses 02 and write. So master will think that this is hot join request, and it will initiate the enter dynamic address assignment or any other method to assign the dynamic address assignment. So that slave can uh, sometimes some requirement will be like that. To save the power, it will go in low power mode, or it will disconnect from the network, and after some time it will again wake up and it will ask for the dynamic address assignment. In that case, master can preserve all dynamic address, and next time whenever that slave is asking for dynamic address, it can give same dynamic address to that slave. So there is, yes, in this, in I2C, there can be multi-master, but it was in the open drain mode. But here, uh, there is method to handshake between master and the secondary master. So here also same procedure is there, that secondary master will pull STL line low, and it will give its own dynamic address on the bus, and here it will give write bit. In IBI it should give read bit, but this is mastership request, so write bit will be 0, and that main current master will give acknowledgement, and next step is it will send the get accept mastership command, where it will send this command, and it will give the dynamic address of that requested secondary master. And in this phase, that secondary master should emit its own dynamic address, and it should be stop condition after this command. Then only it will transfer ownership to the secondary master, and that secondary master will become current master, and after that it will do all the operation like main master. From here onwards, I'll request Godfrey to continue with this.
Yeah, thank you. Thank you, Brijesh. So let's look at how do we test the devices and what are the requirements. Now, if you look at there are two layers, right? One is a physical layer, and second one is a protocol layer. So we will look at the characteristics of IO devices and the timing requirements for different buses like I2C and I3C bus in open drain and I3C bus in push-pull mode. So these are the different requirements at the PHY. Then we need to look at the protocol layer testing. How do we test I3C slave, I3C master, and I2C legacy devices? Can we do some error injections to look the stability and the robustness of testing, the margin testing? Now also I3C is now being adopted by JDEC, DDR5 kind of applications. How do we test those PMICs and SPD devices? Some of those things we will go through that. So let's look at the DC characteristics of the I3C bus. So the operating voltage can be like typically from 1.2 volt or 1.8 or 3.0, but there is a range, a min and max, and so it should operate within that range. Then you have what is a VIH, VIO, VOL, those kind of parameters. These are the DC characteristics of the I3C bus. So these are the some things which to ensure the reliable and very good interoperability, all the devices should be within those devices, within those specifications. Then you have a timing requirements like what is the clock frequency, like this is the I2C timing requirement. There are around 14 to 15 different timing parameters one has to measure and make sure that all these specifications are within the limits of I2C. One for fast mode of the I2C, that is up to 400 kilohertz. And if it's going to work at 1 megahertz, that is a fast mode plus mode. So these are the limits and the specifications, like hold time at start and clock low period, high period, the rising edge, falling edge, burst free time, that is between the stop and the start of next condition. There has to be minimum time has to be maintained at different speeds. So these are all the different parameters, and the master and device need to maintain those parameter specifications. As a designers and vendors who provide these kind of devices, so it's the responsibility of those suppliers to make sure we measure these, characterize it for different operating conditions and the power levels, and make sure that your devices is complying to these specifications. These are the I2C. Then you have a I3C timing measurements. So I3C, again, they have around 10 plus measurements at different operating conditions. This is an open drain, actually. At the open drain mode, the fall time and the clock after start conditions. So these are all the different parameters one has to measure it. So in order to need to measure it, one has to understand the specifications quite well, and then also need to know how to capture these signals in in a test equipment like oscilloscope, because most of the time these are best measured on a oscilloscope kind of a tool, because they have a higher timing resolution. You can sample these signals at a very, very high speed and identify the VIH, VOL. These are the threshold levels to make these measurements, and identify the start and stop conditions. So protocol level decoding you have to do, so that you can get to those specific areas for this measurement, like where do I make clock start condition. So first you need to identify the start condition in the waveform, and then you need to look at, okay, what is the parameter there, and you need to have a good enough sample rate to get to the resolution of 38.4 nanosecond kind of measurement requirements. So these are the open drain measurements. Then you have a I3C timing measurements for push-pull mode. Okay, so again you have a 10 plus measurements, or no, all these measurements one has to do at different conditions and running different protocol packets, and you need to look at the measurements at a very fine resolution and at a different protocol condition again. So this makes it a very time consuming activity, and also needs a very high level of expertise in the physical layer information as well as at the protocol layer information. So this is a 5-layer how one has to look at the DC IO characteristics and timing parameters. Now next level of testing of the I3C slave devices at the protocol layer, right? So if you are designing a I3C slave, then you need a master which emulates a master, I3C master, and should be able to operate all the operating voltages starting from 1.1 all the way to maybe 3.5 or 3.6 volts, with the flexibility to vary the voltages. And also you might have seen the different timing parameters at open drain and push pull and I2C. So you should be also able to drive your master with all these varying timing parameters to make sure that I3C device is capable of meeting those specifications. And also you need to send different commands, common command codes like enter dynamic address, which we talked about, the in-band interrupt and the hot join capabilities. So whether the slave can support all the common command codes which are there in the I3C basic, I3C 1.0 specification. So all these things needs to be tested, and the error injections, so the margin test capability. So all these things are the I3C master emulator should capable of doing these activities. Then you have a requirement to testing the masters. When you want to test a master, you need a slave emulator which can generate similar things like varying the voltage, timing parameters, respond to the common command codes, and generate some protocol layer errors and interrupt capable, hot join capable. So all these things should be a part of the I3C slave emulator, so that it gives you a complete robust testing capability for you, so that you can check your master whether he's able to can handle all different requirements and all different situations of the I3C slave operation. So now then comes the I2C legacy, because I3C bus can support I3C legacy devices. So we should be able to connect a I2C legacy slave device to a I3C master emulator, and make sure that it supports all the voltages and timing parameters of the I2C specification, and do some read and write operations, and the margin testing capability, and the NAC and NAC acknowledgement and NAC kind of features. So all those things should be the I3C master emulator should be able to support it in order to test a I2C legacy slave. So now coming to the emulating the I3C bus. So the I3C bus in overall, if you look at it, it will have a master and a multiple slaves. But when you are only designing a slave, but you would like to have a multiple slaves in the bus and one master, so how do we do that, right? So that's a one challenge. So you need a master or a device which can emulate a master and slave at the same time, and capable of generating a real world traffic, like we should able to put some data on the registers and the slave should be able to read it, or master should be able to read it. So depending on the requirement, and it should be capable of almost generating a traffic like a real time and able to generate some error messages. So these are the requirements when you want to check a slave on I3C bus. Now, in case if you have a master and a slave, everything is in system ready, which are all communicating each other, and you want to monitor that, then you want your device, the test equipment to be a sniffer, right? So you should be able to just hook up to the clock and the data line of the I3C bus and monitor continuously over a long period of time what kind of traffic is going on between this I3C bus, what are the error messages, and those kind of activities you may like to see. And so many times, like you also like to capture the traffic at a specific event or notify an event as and when it's happening in the real time. So you would like to have a real-time trigger capabilities in the I3C exerciser and protocol analyzer, or you may like to have a I3C sniffer, which should be a part of your this whole product. So these are the capabilities required in order to thoroughly test the emulating I3C bus. So these are the different requirements for testing a I3C devices like master, I3C slave, the legacy I2C devices, and also emulating a network. So let us quickly take a look at the demo of the I3C testing. Let me share that video with you. So Brijesh, I would request you to give a commentary, and can you video you can see, Brijesh?
Yes.
Yeah. Okay. So let me start the video playing it. Yeah.
So here is our software view where you have to first click on the connect button, and you have to first configure the bus. So we have option like one master, secondary master, and 3 slaves, and also interface like internal to our box or external device like your DUT. After that, termination on and off. So it is for pull up on or off. And in our device we can enable one master, one secondary master, and 3 slaves. So in I3C slave we have different registers as per the MIPI spec like BCR, DCR, and PID. So we have to first configure that, and this information we have taken from the MIPI website, all the vendors name and what are the DCR register values. First we have to configure for external or internal slave. Here we will give internal master and internal slave. After that we have analyzer also. So whatever activities is going on the bus, so that we are capturing and we will display here. So we have some script. So we can vary the open rain, clock frequency, T-cast value. We can change the duty cycle. After that, we can change the push-pull frequency, duty cycle. After that, we can change the clock to queue delay in a resolution of 18 picosecond. After that, here some set of commands are there. As I mentioned earlier, first we have to give the dynamic address assignment. So dynamic address, after that some registers we are reading directed, get MRL and get MWL. After that I am using one broadcast command to set MWL and directed command to set MRL, and we are reading some registers, so and some private read write command. So you can build your own script, and in one shot you can send these commands on the bus. So get MRL value is 0 and 10 by default. After that we will, you can see on the plot view also there is a bus diagram. So once you click on the decoded result or frame view, it will be appropriately updated, and we have bits overlaying. So you can see ones and zero as per the clock rise edge. After that, we are reading get PID, get PCR, DCR register. And in our software, you can put unlimited markers and you can measure the time between two markers. Get DCR. After that, previously it was 0 and 10. Now it got changed because we have set the MRL value to 10 and 00. MRL is 20 and 00. And after that, private message with data 1234, and we are reading back same data. And we can, this, as you can see in the selected frame view, frequency is 12.5 megahertz. You can put cursors and you can measure the high time and low time. High time is 40 and total duty cycle is 80 nanosecond. And it is read command, so it will give same data on the bus. After that, you can clear the results. So whatever is captured on the bus, it will clear, and you can run another script, or you can, without clearing also, you can run the script. So here we are doing private read write message with loop count 5. So whatever script you have given, it will run in the loop for 5 times and it will execute it on the bus. So as you can see, we received private write and read command, 10 total commands. So we sent 5 write commands and 5 read commands. Here in decoded view, you can see the who is sending the data. Like first address is initiated by master and read data is initiated by the slave. So from our slave, you can generate IBI request, hot join request also. So here I am generating IBI request. So it has sent mandatory data bytes 1 and 2 on the bus. So as per the mutual understanding between master and slave, master can send some read commands and it can read some registers from the slave and it can clear that interrupt. So now I will add another slave to demonstrate hot join thing. So we have added. So now currently one master and 2 slaves are present on the bus, with one slave already got dynamic address assignment 8 and this slave dynamic assignment is pending. So this can generate hot join request on the bus. So we will load a hot join script. Now I am initiating hot join command from the slave 2. So it has sent hot join request with address 02, and after that our master has given dynamic address assignment to that slave.
Okay, so let me go back to the PPT. Sorry, I think. Yeah. So let's look at the solutions, what is available from Prodigy. So the requirement here is that testing I3C bus is like DC IO characterization, timing characteristics of I2C bus, timing characteristics of open drain operations in I3C. Similarly for push-pull mode. And then you have a master I3C master emulation, I3C slave emulation, legacy I2C slave emulation, I3C secondary master, and I3C bus. So all these the generation capabilities are available with the PGY, I3C exerciser and protocol analyzer. And as far as the electrical measurement is concerned, we provide softwares which run in Tektronix oscilloscope for I3C as well as for I2C. They support both open drain and push-pull modes. And then for all the analysis part of the protocol, for error checking, everything, and the sniffing purpose, so you can use the same PGY, I3C, exerciser, and protocol analyzer. So almost we provide a very comprehensive solution to take care of the physical layer and the protocol layer requirements, including the protocol analysis as a sniffer. So this is about what we wanted to present about the basics of I3C protocol, as well as the testing requirements of I3C devices. So we have been involved in MIPI interoperability from the very beginning. All this product is tested thoroughly or across a long period of time. So we have around Asif, I will pass. You can now take over the presentation.
Thank you, Godfrey. Yeah, this is Asif here. I'm your host. Yeah, so now what we're going to do is we're going to open up for the question and answers. So people who have question and answers can start typing in their questions directly on the Q&A, and I'm going to read the questions one by one for you. Please, and people who want to ask question can quickly raise their hand. People who, yeah. So we are opening up. Yeah, so I think I'm getting some questions. So in the meantime, let me ask some questions here. So with respect to this Prodigy I3C product, right? Has it gone through I3C interoperable testing?
Yeah, like Prodigy Technovation has been involved with the MIPI I3C. We are also a contributing members, and we have been participating in all the I3C forum over a long period of time. Almost we were there for every interoperability, and product has gone through a very extensive interoperability test, and it's been successfully adopted by some of the top semiconductor companies.
Okay. And does it support error injection?
Yes, PGY I3C EXPD supports error injections capability. You can do error injection for protocol layers like parity error, command errors, and I think some more errors it can inject. Yeah.
Inject. Okay. I have another question. Is it possible to perform timing parameter sweep with a test solution?
Yes, you can also vary the timing parameters of different parameters. Yes, you can do it. You can also sweep it using the loop mode. Brijesh, you want to add anything onto this?
Yes. So we can change the frequency from 1 kilohertz to 12.5 megahertz in a step of 10 nanosecond. Okay. After that, we can change the clock to Q delay. So with that you can change. You can check your setup time and hold time threshold. After that, we can change the, like, we can insert the stop parity, stop error, repeated start. There we can change in a step of 10 nanosecond. So after that, TCAS we can vary in a step of 10 nanosecond. So these are the parameters you can vary. Only thing is we cannot vary rise time and fall time. Other than that, whatever parameters is mentioned in the spec, almost all parameters we can vary.
Okay. So I have a couple of more questions here coming in from our participants. So I'll read it out for you. So until the hardware is available, we are developing a system on a simulated environment running on a PC. We would like to use exercising unit to provide the I3C interface for this test system. Does the unit provide the appropriate interface?
Yes, yes. Let me take that question. We supply the unit with two sets of flying lead cables with a female header pin. So with the coax cable, you can go up to all the way up to the maximum speed of 12.5 megahertz. With the appropriate ground, it works perfectly with the customer DVT, real DVT.
Okay. I have another question here. I3C or CAN, which is the preferred in industry, and efficiency of I3C versus CAN? I guess that's a question one of the participant is asking.
Yeah, I think that's a question. Maybe I'm not an expert in CAN, but CAN is more targeted towards the automotive bus, and it's a differential signaling. So I'm not sure the commercial sides of it. It may be much more expensive, I feel, in terms of IOs and all. And it's also more of a deterministic bus. I3C is a single-ended signaling, and it may be much simpler, very similar to I2C. Preference is, I think it is left to the design community because it depends on the application where they are using. There may be some applications I3C is well suited, but there are some applications which is CAN is well suited for those applications. So we may not be able to comment which one is better, but it's a very design specific, I would say.
Thank you, Godfrey. I have another question. Is the feature of HJ is independent to IBI? So if my device does not support IBI but supports SJ, should my register BCR1 register default values to be set to 1? Okay, that's a question.
I think this is a question for Brijesh.
Yeah, and there's one more thing. One next following question on the same thing is what is the feature necessary for all the I3C devices, master and slave? I think you can answer both of them together, Brijesh.
Okay.
One is a very technical question.
Yeah, first thing is I think actually internally hot join and IBI is the same. So whenever you want to give that request on the bus, then I think you should set your BCR first bit register to 1. Then it is capable of generating the IBI. Only thing is internal mechanism will be same. And next was what
Yeah. So what
feature is necessary for all
what the
like
feature is necessary for all the I3C devices, master and slave? What's a must-have feature? That's what
must have is like that should support enter dynamic address assignment and some device characteristic registers like BCR, DCR, and some status registers should be there in that I3C slave, and IBI means that also depends on the application to application. If your application is means you have, let's talk about sensor, one is temperature sensor and another is a heartbeat sensor or something. So in temperature sensor there is not that much critical, so if you don't implement IBI and all, that is okay, but in heart rate sensor it is more critical, so you should implement that feature. So this is like it depends on what kind of application it is, but enter dynamic address assignment and directed and private is must.
Yeah, so we are kind of running out of time. I'll just take the last. Okay, I think he's still asking the question. So what we can do is, I'll just take one last question, and I'll give you our email ID where you can write to us and get more details. Here the question is, if we have a system with one master and few slaves, he's put in bracket NEM, not working properly, how do we find out the root cause? PHY or protocol with your products?
Okay, let me take that question. So first of all, I think it is better to approach by the protocol layer problem. So it is better to do a protocol analysis by using the sniffer mode and look at the different packet communication between the master and slave from the enter DA mode onwards. And then I think you get a good picture of where is the problem, right? So once we have the problem, depending on that, I think then we can decide maybe do a electrical measurements, and then we can know that exactly, okay, whether that protocol error is caused by the timing problem. In the protocol in Prodigy's PGY I3C EXPD, you can also make quite a good amount of timing measurements using the product itself, so that you can know the timing problem also. So it's kind of difficult. Like, debugging a problem is always there is no standard set rules. So I would maybe suggest that if maybe we can approach it from the protocol layer, then go to the file layer if we cannot locate it in the protocol layer.
So this is another question. I think in the interest of time, what Godfrey, what you can do is we can share some email ID so that people can write the questions.
Yeah,
down.
sure, yeah.
So I think thanks. So I'm going to type this contact@prodigytechno.com. I think.
Brijesh, can you change the slide?
Can you put that email ID so that I think there are some questions there coming.
Last slide.
Yeah.
It's not sitting.
Okay, you can type it there, or yeah. So I'm going to type it into all the attendees.
It's contact@prodigytechno.com.
Yeah. So yeah.
Yeah. Okay.
So that's our email ID. So if there are, I know Owen Young, you have some specific questions. You can actually write to us there, and we will connect you to Brijesh, who can work on with you one-on-one to help you explain the issue or help you debug that particular issue separately, right? So in the interest of time, we are going to wrap up the session, and thanks everyone for joining. And thank you, Godfrey, and thank you, Brijesh, and Chirag for helping host this conference. And hopefully we are going to have many more conferences in the upcoming quarters. And you'll be hearing from Prodigy from time to time. Please follow our newsletter and our emails as we update to you. Thank you, everyone. I'm going to stop the meeting right now. For any queries, please contact us at our email ID, contact@prodigytechno.com. Thank you. Bye.
Thank you. Bye.
Thank you, everyone. Bye-bye.